This mini lecture and example will illustrate the methodology required to do a integral that leads to an inverse trigonometric form, and specifically the inverse sine form. So in the problem-solving methodology for integration, this is actually step 5. And in step 5, when you're doing integration, you ask yourself the question, does it look like, or can it lead to an inverse trigonometric function? And so I'm going to talk about the first of the two forms that we're going to examine in this step. The first form is the inverse sine relation. So remember that when you have the derivative of arcsine of any argument, that the derivative of that statement from the first half of the course was 1 over square root 1 minus argument squared times the derivative of that argument. And so this form, if we treated this exactly like the standard trig forms, all we would do is we would rearrange this equation into its differential form, so that the differential of arcsine u, if I multiply both sides by dx, you'll end up with du over root 1 minus u squared. And then if we integrate both sides, so I'll just switch sides and integrate. So if I integrate the du over root 1 minus u squared, then that will be the integral of the differential of arcsine u. And on the right-hand side, the integral and the differential process are both applied to one function. Those inverses cancel each other out, and so we would end up with the result arcsine u plus c. So we end up with this form, integral du over 1 minus u squared square root, is arcsine u plus c. The problem with this form is that it is extremely specific. The number that is in this difference of squares that is in the square root is exactly 1. And so how often is that actually going to come up? And the answer is not very. And so we need to have a more general form for this solution that allows us to have any number here, not just specifically the number 1. And so what I want to do is I want to solve this form. I want to solve what is the integral of du over square root a squared minus u squared, so that I get in this denominator a difference of squares. A difference of squares where I have a is a number, so a is a constant, any constant I want, and u is any function that I want, some function of x. In order to solve that integral, what we would do is we would try to make this look like this form, because we know the answer for this form. And so I can do that. I can change that a squared into a 1 just by factoring it out. So if I factor out the a squared in the denominator out of the two terms that are in the difference of squares, if I factor out a squared out of a squared, I'm left with 1. And if I factor a squared out of u squared, I'm left with u squared over a squared. Since a is a constant, and it's a perfect square inside of a root, we end up with just a single a on the outside of the expression. because constants can multiply constants can come outside of the integral, we end up with this 1 over a integral of du over root 1 minus u over a all squared. Now if you compare this form to this form, you'll see that now they are extremely similar. And in order to make them identical, I can just do a simple substitution. If I let r be the relationship that is inside of this bracket, u over a, the differential of that, since a is a constant, I'm going to end up with 1 over a times du. And 1 over a times du is exactly the differential that I've got in this problem. That's 1 over a times du. So when I do my replacement, I am left with dr on the top takes the du over a and replaces it with single term dr. And in the denominator, I have square root 1. I didn't touch the 1. I didn't touch the square root. Minus r squared. Remember, when you do simple substitution, you do not have to replace for all the functions. You do not have to replace for all the powers. All you have to do is replace for all the variables. So this variable u has to go, and it is replaced with variable r. Now this form is exactly this form with an r instead of a u. So we can go right to the answer. The answer for this is arcsine r plus c. So the final solution then, if I undo the substitution, is arcsine u over a plus c. And that's the solution to this integral standard form. So this effectively becomes just like step 3. We've basically expanded our list of standard forms by one more. We've taken the original derivative of the Arcsine relationship and made it just slightly more general by allowing us to have any number in that difference of squares. So this is effectively what you do in step 5. You look for this specific form. Is it a difference of squares in the denominator of a fraction inside of a root where the leading coefficient is a constant? It is not the function. So the number here comes first. If you check all of those boxes, you have to see a square root, you have to see a difference of squares, and the number has to be first in that denominator. Then you would try to use this form as a standard form. So you would do a simple substitution to get it into exactly this form and then write down the answer. So to illustrate this with an example, if you had to solve the following integral, I equals integral of 4 e to the 3x dx over square root 9 minus e to the 6x. Okay, this is a question that is very similar to the difficulty of questions you see on unit tests and finals in this course. You go through your standard technique. Step number 1. Is this a simple power of x? The answer is no, because there are transcendental functions present. There are exponential functions present. Step 2. You look for a function differential relationship. Now it turns out there is a function differential relationship here, but it's kind of easy to miss. If you look at 9 minus e to the 6x, the differential of that expression would be the differential of any exponential is itself times the differential of its argument. So the differential of 9 minus e to the 6x would be minus e to the 6x times 6, not e to the 3x. So there is a disconnect there because the argument of this exponential does not match up to the argument of this exponential. So it doesn't really look like there's a function differential present. Step 3, is this a standard form? Is it one of the 1 over u integrals or e to the u integrals? And no, we've got this weird square root thing with multiple terms in the denominator. Is it one of the standard trig forms? The answer is no. It doesn't look like any of the standard forms. Step 4. Does this, or can this be done with trigonometric identities? So you look for trig functions in non-standard form. There are no trig functions here. Therefore, we can't use the identity steps. You just skip that step entirely. Okay, now we go to step 5. Could this possibly lead to inverse sine? Could it possibly lead to inverse sine? All we have to do is check. Do I see a square root on the denominator? Yes. Do I see a difference of squares? Maybe if I rewrite this into square form, I might see something. And is the number first? Yes. So let's check this. If I just rewrite this problem, doing nothing except rewriting the terms in that root as perfect squares, I can rewrite 9 as a perfect square. That's 3 squared. And I can rewrite e to the 6x as a perfect square. I can write that as e to the 3x all squared. Remember your rules of exponents. When you multiply, when you raise an exponent to a power, you multiply those powers together. So e to the 3x all squared is e to the 6x. Suddenly, look what has happened. The e to the 3x that is in this bracket is now, there's now a function differential with the e to the 3x dx that is in the numerator of this expression. So if I do the following substitution, let a equal 3, because that is the factor, the constant that's in front, as a perfect square in that difference of squares. And then I'm also going to let u equal e to the 3x. The e to the 3x that's in the denominator. The differential of e to the 3x is e to the 3x times 3 dx. But I've got e to the 3x dx by itself, so if I divide both sides by 3, I end up with a direct substitution. For my numerator, e to the 3x dx is replaced with du over 3. So, the multiplied factor of 4 can come out front of the integral. Inside the integral, in the numerator, e to the 3x dx is replaced with du divided by 3, and the divide by 3 can propagate out front because it's a multiplied constant. In the denominator, we did not touch the square root. It is still there. 3 was replaced with a, so we end up with an a power 2. And the e to the 3x in that denominator is replaced with u. So we have u power 2. By just doing a simple substitution, this has led to a standard form. This is the form that leads to inverse sine. So I can immediately go from this to the solution. The answer for integral of du over square root a squared minus u squared is arcsine u over a plus c. My function is now solved. I've solved the integral. All I have to do is undo the substitutions to get back to my original variable. And so u was e to the 3x, and a was 3. And so here is the solution to the integral. 4/3 arcsine of argument e to the 3x by 3 plus c. Remember, when you do integrals like this, you have to see exactly the difference of squares in the denominator with the differential of that variable function u up top. If it is any other pattern where you've got a square root on the top, or this is a plus sign, or it's u squared minus a squared, it is not the arcsine form. It has to be exactly this form. If I've got a u on the top as well, then that doesn't make it this form. It has to be exactly this form in order for this to work.